Alright, so we're continuing 5.4 here with calculus. And what we have is the position, and I warned you in the first video that sometimes I write S of t, and a lot of AP stuff does, textbooks do, which if you want, you can always, if you define it differently as P of t, that's fine. As long as you show, like if the directions define something as S of t, then you should use S of t unless you decide to go back and rewrite, like let P of t equal S of t. So anyway, as you look at this problem, and they ask you at what point does the velocity equal 0, well, think of the relationship between S of t and velocity, and that rule is S prime of t is equal to V of t, and since the directions want you to say that V of t equals 0, we want the horizontal tangent. Well, I would say at B. I would also say at D. So at points B and D. At which point does the acceleration equal 0? Now, a little bit more difficult to justify this one, but the whole premise is that the second derivative of position is equal to the first derivative of velocity, which equals acceleration, not a 0 there, A of t is equal to 0. In other words, we're sort of looking for a point of inflection. And I would argue at point C. And maybe I should clarify up here with B and D that those are relative extrema. That might be a better thing to say than clearly it's the velocity is 0, something like that. So there's multiple points then where the particle's velocity is positive. Well, if we're examining where the velocity is positive, that's the first derivative again, is equal to velocity, and we want that to be positive, so we want where the function, where S of t is increasing, and I would say that is at points A and E. And likewise, when we look at the velocity being negative, really the same reasons, S prime of t, V of t, but now we want that to be less than 0, where S of t is decreasing. I would argue that that is at point C only. And you go back, that definitely not equal to 0, so we want the one where we're decreasing to the right. Or the acceleration is positive, a little bit tougher to explain this one, but that would be where the velocity is increasing. And maybe it would be worthwhile to kind of go back to the section where we talked about, if this is position, we could graph the derivative, where your extrema are, and then it's increasing, so it would be there, to decreasing is below the x-axis, and increasing to the right is above the x-axis. So that's the graph of velocity. And then from that, you could say, oh, okay, well, here's my relative extrema, lined up with C, by the way. It's decreasing first, so below the x-axis, and then increasing to the right, above the x-axis. Trying to make it so you can actually see that blue is acceleration there. That's a very poorly drawn graph, but I think you get my point. So then from that, I think you can tell clearly that the acceleration would be positive at points D and E. So particle's acceleration is positive. So if acceleration is greater than 0, maybe another way to explain it is if the acceleration is positive, then the curve that we were given, that S of t, must be concave up. And at those points, that might be easier to explain, is at D and E. But I think my graphs also explain it. And I could say the same thing about the last one, where acceleration is negative. So S of t is concave down. I think it's A and B if I remember correctly. Yeah, A and B were concave down. Perfect. Again, I'm going to go to the answer key just because I don't want to mess anything up. So all of these answers are based off of horizontal movement. He's talking about movement on the x-axis, left and right. So what you want to make sure that you can either deduce on your own or memorize. I'm more of the remembering, like the thought process, not memorizing, which kind of sounds counterintuitive now that I say it out loud. But think about, what does it mean for velocity to be positive? Well, then the object is moving, but in what direction? Well, the positive direction would be to the right. If we have a negative velocity, it's to the left. Now, this is a new concept for you, speed. Speed is always positive, all right? Like speed and velocity, very similar. Velocity gives you a direction, though. So you can have a negative velocity. You will see questions that ask you if the speed is increasing or speed is decreasing. The easiest way to remember is speed is increasing if the sign of velocity and acceleration are the same. Think about if you're in a car and you have a positive velocity and you step on the accelerator, then both your velocity and acceleration are positive and your speed is going up. Now, if you are driving in a car and your velocity is positive and you press the brake, acceleration would be negative at that moment. Well, if your velocity is positive and you hit the brake, your acceleration is negative, your speed slows down. So that's why the signs, if they are opposite. Students always confuse this, so I'm going to say it slowly and maybe it makes sense, maybe it doesn't. If your velocity is negative and your acceleration is also negative, then your speed is still increasing. Think about if you're in the car and you're backing up. Well, if you're backing up and you press the accelerator still, your acceleration is technically negative because you're moving backwards. When you hit the brake there, so you've backed out of the parking lot, whatever, when you hit the brake, your acceleration is actually positive and makes you slow down. So when your velocity is negative and your acceleration is positive, you do slow down. I think I've covered all that. So a lot of students memorize these two things. And all your reason has to be for speed to be increasing is both sign and acceleration. The signs of velocity and acceleration are the same. You can either say both positive or both negative, but they just have to be the same in order to be speed is increasing. And then speed is decreasing if you have opposite signs. And then the last thing, if the velocity is equal to 0 but the acceleration is not equal to 0, then the object is momentarily stopped and changing directions. That's just talking about like your relative mins and maxes. By the way, we don't always use the phrase, we are stopped. Sometimes we say when the particle is at rest. So be ready for some of those key terms as we move forward. So go ahead and pause this as I go back to our notes. So we have this problem. I don't believe we need a calculator to do this. We'll see. But notice that they give you the velocity. And we can answer these following questions. So find the values of b of 3. Well, if we were to plug in 3 in for both these, well, I don't know, maybe you would want a calculator. So b of 3, we'd have 5 there, and then it'd be 7 squared. Maybe we would want a calculator. So if we're going to use a calculator, we might as well just plug it in exactly the way we would, x plus 2, and then x plus 4 squared. There we go. So quit out of that. Alpha trace y1 when x was 3, right? All right, perfect, 245. Now the reason why I went ahead and just did that, if I'm going to use a calculator and I'm finding v prime of 3, you know, that's the same thing as saying what's a of 3. And I trust that you guys could find the derivative of that. It's the product rule and the chain rule, although this chain rule, the derivative of the inside is just 1. But as I mentioned, since in y equals, I already have the derivative of that written out. In the home screen, all I have to do is hit alpha trace of y2 at 3. And I got 119. I don't know if that's exactly, but I would round it there anyway. So based on these, what's happening for the speed? Well, all we care about is that this is positive and this is positive. So we can deduce, because they are the same sign, since velocity and acceleration are both positive, same sign, speed is increasing. And then what we can do now, and I would not use a calculator for part B. I would like to see your sign analysis. So I want intervals of particle moving to the left, to the right, and show your sign analysis. I actually kind of have an issue with this, is because all of these are positives, but the sign analysis, you would put -4 twice for your multiplicity, and -2. But what's awful about this problem, I really don't like this, is values for t are we only care about values bigger than 0. So this is a very, very poorly written problem. But if you were to do this, you would put -4 and -2. And you may remember this from last year or earlier in the year. So had we actually done this, it would move to the left, velocity being negative, still moving to the left, and then this would be positive. And everything to the right is actually, so for t greater than or equal to 0, this object is always a positive velocity, which means it's always moving to the right. And I'm going to go to the answer key just because I'm kind of second guessing how poorly written that question is. Yeah, that person didn't even bother doing anything to the left. And I don't even like his work because his sign analysis does not include all values. But that's a whole other argument. So I want to see something like this. But since velocity is greater than 0 for all, upside down A means for all values for x greater than 0, particle moving to the right. All right. Now I think I'm going to just have you work through these problems. And maybe what I'll do is have this be like a part 1, ask questions in class, in Google Class, and then 5.4 homework. And then I'll do some more. So don't forget, any of these problems can be found on the internet. So just look up the year, look up, obviously, AP Calculus AB for your responsive practice, and you should get some sort of answer. Now notice it says modified, so it might be slightly different, but you can reference that. And we can talk about this in class as well.